Hello everyone, welcome to the DLA practical series. Today we'll be doing the topic that is 3-bit ripple, that is asynchronous and synchronous counter using IC7473, that is the JK flip-flop, and some required gates. So what is a ripple counter, or we say asynchronous counter? So ripple counter is a cascaded arrangement of flip-flops where the output of one flip-flop drives the clock input of the next flip-flop. So cascading means what? Output of one is given to the input of the other. So in this case, the clock is applied to the first flip-flop, and the output of that flip-flop becomes the clock of the next flip-flop. So this is actually called a ripple counter because the way the clock pulses ripples its way through the flip-flop. Therefore, this is called as a ripple flip-flop, ripple counter. Sorry. Now, what are the salient features? There is a asynchronous counter. Okay, so why it is called as asynchronous counter? Because the clock are not applied simultaneously to each and every flip-flop. Okay, the clock is applied to the first flip-flop, but the output of that flip-flop becomes the clock of the second. So the main clock is not applied to each and every flip-flop, the first flip-flop, only the first flip-flop. So all the flip-flops are used in the toggle mode. That is, both the inputs are J and K, both are given to the connected to the VCC, that is, they are at logic 1. Only one flip-flop is applied with an external clock pulse, and another flip-flop clock is obtained from the output of the previous flip-flop. So then what is the meaning of a synchronous counter? Now synchronous counter is a cascade arrangement of flip-flops where output of all flip-flops are driven by the same clock at the same time. So all the flip-flops, they are driven by the same clock pulse. Okay, so this the features is that it is a synchronous counter and all flips are not used in toggle mode. Okay, so in this case the flip-flops are all the flip-flops are not in the toggle mode. Okay, now this is the diagram of a 3-bit asynchronous, that is ripple counter. So here if we have this 3-bit means we require 3 flip-flops. So as we see, VCC is connected to J and K of all the flip-flops, and clock, okay, the clock is applied. As you can see, this clock is applied to the first flip-flop, and output of the first becomes the clock of the second, output of the second becomes the clock of the third one. Okay, and when the count progresses, when we start this working of when we start the clock, okay, we get this output. Okay, when you turn on the circuit, we get this output from Q0, Q1 and Q2. So 0 0 0 0 0 1 0 1 0. So it completes. This is a counter because it is counting states from 0 to 7, then it again goes to the reset state. So these are the states. Okay, similarly for synchronous, this is the diagram for a synchronous counter. We are using, this is 3-bit synchronous. As we can see, the main thing is here, the clock is applied to each and every flip-flop. Okay, and all the flip-flops are not in the toggle mode. Okay, so this is the diagram for implementing the 3-bit synchronous. So we are using some gating circuit. This is the AND gate is used. Okay, this is the diagram, and output is of course the same as we got in the previous case. And we will see this. This is the, we can say, the timing diagram. The first wave, the upper one, is the clock pulse. This the second pulse. The second wave diagram is of the first flip-flop. This is for the second, and the last one is of the third flip-flop. As we see, the time period goes on increasing. The time period of the third flip-flop is twice that of the second, which is twice of the first, which is twice that of the clock pulse. So this is the output we'll get. Now let us design this on the multisim software. So we turn on the multisim software. So first of all, we select the JK flip-flop. So we go here, and we can go to the, we can even go into the miscellaneous digital. Okay, and then select the JK flip-flop from here. Okay, this is of nothing but it is the 7473 IC. Okay, we can directly select this. We'll just select this. Okay, then we need a power supply VCC, power source is VCC. Okay, so actually we need 3 JK flip-flops. So this is the first one. Okay, then we have, this is the second, because we can get it from here itself. This is the second one and the third one. So 3 JK flip-flops. Okay, then we require a clock. Now where to get the clock? So click here in the sources, and below power source we have signal voltage source, and here this is the clock voltage. This is the clock voltage. You select the clock voltage here, keep it here. Then for the clock voltage we also need a ground connection. So we come back to the power sources. So here VCC, above VCC you can see here this is the ground. So take the ground, okay. And now we do the connections, okay. So first of all we need this JK flip flop in the toggle mode. So we need to connect this VCC to each and every input of the J and K of all the flip flops, okay. This is the simplest way which we can connect, okay. We do this connection. So this one and this one, okay. Then we connect the clock to the first JK, okay, and connect this to the ground, okay. And this output of the first becomes the clock of the second. The output of second becomes the clock of the third one. So this is the connection, very simple connection. Now to check the output we need a CRO. Let us see where we can get the CRO. So for the output we need a CRO. So here you can see on the right, extreme right, this we have some devices, okay. So this is the first one, second, third, fourth, the fifth one, okay. If you click here we get this, okay, the fifth one, okay. Now we need to connect this, okay. There are, in this particular CRO there are 4 terminals A, B, C, D. So we need to connect these terminals. So what we do is we connect this A part, to the input of the clock. This is the clock input, okay. Then B is connected to the output of the first flip flop. C is connected to the output of the second flip flop, and D to the output of the last flip flop. And you can see there is a ground connection here, the common ground connection. We connect it to the ground, okay. So this is the connection we do, okay. Now after the connection we run the simulation. So I'll just click here, okay. And now this is running. How to check the output? We'll just double click on this CRO. Here we get this type of, okay. So all the 4 waves, because there were 4 channels, so we have 4 waves are all jumbled up. The very first thing we do is we just reverse it, so that we get a white background and the red wave. Now here as you can see this knob is at A, okay. This is A, this knob is at A, okay. So we just pull this up, Y position up. So we have to separate all the 4 waves. So I just pull it up, okay, the A part. Then I click this knob on B, okay, and take it a little bit up, Y position. Sorry, I'm just sitting. So this is B, okay. Then we click on knob C, taking the knob on C. We just take it down. This is C, okay. And then we click on D, okay, and pull it down. So all the 4 waves, they just separate out. As we can see, these are the 4, okay, waves. I'll just click on C and just adjust it properly so that all the 4 waves are visible properly on D, okay. So we can also increase the scale, the X scale. So I just click here, so decrease the scale. I'll just decrease the scale, okay. So this is the output. This is what we are getting, the output. Now in the output, as we can see, the first wave is the clock wave, the second is the output of the first flip flop, the third wave is the output of the second flip flop, and the fourth wave is the output of the last flip flop. Now the time period, as we can see, the time period of the last flip flop is twice that of the third flip flop, and the time period of the third is twice that of the first, and the time period of the second of the first flip flop is twice that of the clock, okay. So this is how this is the asynchronous counter works. Now let us see the synchronous counter. Now we go for the synchronous counter. So we require almost the same thing. So I've just deleted the wires. I already connected because this circuit is somewhat different from that. Some little changes are there. So first of all we need a AND gate 2 input AND gate is required. So I'll go in this miscellaneous digital and 2. Okay, I'll just get and 2 here. Okay, just place it here. Okay, and then the very first thing I just do the connection. The first one, as we can see, it is in the toggle state. Okay, this is the toggle state. Then we connect the clock. This clock is connected to each and every flip-flop. Okay, so this, just connect this to each and every flip-flop. Okay, now this output, okay, is connected to this J and this K. Okay, and the output of this is connected here to one of the, and this is connected here, sorry, and this comes to the output here. Okay, so this is the connection. Okay, now one more is there, sorry, this one needs to be connected. Okay, now the connection is done. Okay, now we just connect the CRO. Okay, the first part is the clock, so we connect the clock here. Then the B part to the output of the first flip-flop, this one to the output of the second flip-flop, this one to the output of the third, the last flip-flop. Okay, now I can just run the simulation. Okay, and click here. So now this is the wave we are getting. Okay, the same as the previous one, only the difference is that this is a synchronous 3-bit counter, that was asynchronous. So that's all for this particular session. Thanks for watching.